Welcome to the lecture series in computer science. As a part of this series, this is a course on artificial intelligence and we are in unit 3 now. Last week we have done some examples on the proposition logic, where we were talking about the initial part of the syntax, the semantics, and also a little bit into the reasoning process. So, before we get into these topics, which would be the Wumpus world puzzle with the theorem proving exercise on the top of it, we will be looking at some of the questions that we saw last time. In the last class, this is a quick recap also. In the last class, we have seen the evaluation for some of the formulas. Suppose you take this example where p is equal to false, q as true, and then we can identify as not p and q is true. So, if we have a formula for each of the literals, literal is something that you can take as one single alphabet right here, or one single instance we call that as a literal, and not p, if p is true, then not p is false and q is true, or if p is false, not p is going to be true, q is true, and this expression, the whole expression will evaluate to be true. In that case, we are going to write v is evaluated to not p and q, or v entails not p and q. The other question that we asked last time was whether p and p implies q, that the whole implies q. Suppose we take p as, suppose we take p is equal to true and q is equal to true. If we take these two cases, then this will evaluate to true, and 2 implies true, the whole implies true. True implies true, this is going to be true, true and true, this is going to be true again, and this implies true, the whole expression will lead to true. So, the value with p and q true evaluates to the entire model as true, and v in this case entails this expression. The other one was v, whether it is going to entail not of p. In this case, if you take p as true, not p is going to be false and not p is going to be true. In this case, v models, or there exists a model for v that entails not p. P, suppose you take as true and q as true, p implies q, this would be true implies true, or true implies true. In this case, true implies true, this is going to be true, or this also is true. Therefore, if you take p and q are true, v entails true. Suppose if you take p as true and q as false, what will happen? P implies q will be true implies false, this will lead to false. So, this expression on this side will lead to false, or q implies p. In this case, this would be false implies true. If it is false implies true, this is going to be true, and false or true, this is going to be true. In this case also, if true and false, this expression will evaluate to true. So, v entails this expression, this is valid. Then we went into the evaluation in all possible situations, and we defined what is contradictory, satisfiable, and a tautology. Then we said about the inference. This is an expression, phi 1 is one expression that goes on until phi n is another expression. If we have some facts, these are the proposition, formula, or the expressions. If there are those expression, then the inference I can write as psi, this is valid. So, inference is valid only if in all situation, if phi 1 is true until phi n, all these expressions whatever and then that uppercase is true, and this is not actually the denominator, we will just write it as what is the conclusion. So, this is also true. So, we say that this psi whatever we write down is a logical consequence of phi 1 to phi n. So, we write phi 1 to phi n entails psi. Yeah. These are the models that we did last time, and these are formulas that we will be using again and again for any reasoning process in proposition as well as in predicate logic. Now, last time we talked about a knowledge base. A knowledge base is something, a set of facts, facts that is written in a proposition logic formula. So, example here is Chennai is hot, that will be either with month is May or month is April. This is going to be the by equivalence, this equivalent. And suppose if it is Chennai is hot, these are equivalent to Chennai is hot. All that we did was both, we have combined these two statements with and we can call this as a knowledge base. So, proof methods, there are two ways initially, but we will also be talking about another method called resolution later. But last week we saw the natural reduction rules and model checking with truth tables. We will be going today's exercise with the natural reduction rules. Model checking using truth tables, we will not do it in this as a part of this course, because I will also give you an intuition behind the truth table. The reason why we will not do is, suppose you take an expression something like this. Suppose you take some expression like this, V entails P or Q and Q and P. The number of literals we have is 2 here. Suppose I take another example with P Q R, the number of literals is 3 and P Q R S, it is going to be 4. So, based on the number of literals, the exponential time increases, in the sense the truth table that to be computed, it will be 2 power the number of literals. So, in this case P and Q, it is 4 combinations, which is 2 power 2, and if it is going to be 3 literals, it is 2 power 3, and if it is going to be 4 literals, it is 2 power 4, and for n facts or n number of literals in some formula, it would be 2 power n, and to evaluate in all possible combinations, that is a very difficult process, or it takes exponential time algorithmically, and right now we are avoiding that kind of approach. This course we will be concentrating on two things. One would be the theorem proving, and another would be the resolution. For theorem proving, we will be using this natural reduction rules. We saw last time with some examples like we will be using modus ponens, and we will be using and elimination, and we will be using or elimination, okay, and a few more rules we will be using for the theorem proving exercise. Now, we saw this example last time using theorem proving. Again, I talked about the one example last time, we will solve the second example now. So, for the following statements, prove knowledge base entails girl, we see there are some facts here. Toddler is there, toddler implies child is there, child and male implies boy is there, and infant implies child. If a child and it is female, then it is a girl, then it is a female. Now, can we prove this knowledge base entail girl for this? Okay. So, how do we do that? You take 1 and 2, this I will call as 1, 2, 3, 4, 5 and 6. You take 1, which is toddler, and toddler implies child, with 1 and 2, use modus ponens, we get which would be child, and with this the result of this child and male, another one is with child along with line number 3, which is child and male, it is boy. Use modus ponens again. What is modus ponens? If it is the rule is alpha implies beta, therefore beta, this is modus ponens. So, we will use this modus ponens right here. So, child and male, it indicates boy. The result of this will be boy. This is the first one, this is the second one. And the third one, we have child and female implies girl. We already have this child. Another rule is with 5 and 1 right here. This I will call as 6, this I will call as 7, and this I will call as 8. 6 is a continuous, no, this is 6 already, I am sorry, this is going to be 7, 8 and 9. And this I am just writing the next number after this. And why? Because all whatever I am deriving from these will be added together as a knowledge base. So, 9 along with 5 and use modus ponens, we will get child and female, that female is already here. Okay. So, before it, this will not act this unless this is not going to see child and female, this implies girl, we already get that, but before we get into this. Okay. So, before we get into this, we have to use this female. So, we have child and this female, which is 6, 5 and 6, we get female. How? Use and elimination, which is alpha, and suppose you have beta, use alpha and beta, therefore, we get child and female. And with child and female, with 5 we get girl by using modus ponens. We have child and female, one from child earlier here and another with female here. So, child and female use and introduction, and from and introduction again with using modus ponens for this, you will get girl. Therefore, we will say knowledge base entails girls. So, this is a way that we prove using a theorem proving exercise. Now, in today's class, we will go ahead with the book example of the Wumpus world. In Wumpus world, this is how the puzzle goes. On the right hand side, you would see the puzzle where the agent is going to start at 1 1. This is a 4 cross 4 grid and the agent starts at 1 1. You could see 3 pits here. The pit is something where agent, if he is going, he will fall down and he should avoid going into the pit. And there is a Wumpus at this position, which is at 1 3, 1 is here and 3 is here. So, I will call this location as 1 and 3. So, at 1 3 there is a Wumpus, this Wumpus will eat this agent when the agent is in that particular position as the same as that Wumpus cell. Now, the agent should avoid going into pit or reaching Wumpus. Now, how is the pit identified? The pit is identified by breeze that is just within the neighboring cell across the pit. Suppose pit is at 3 1, this location is 3 1 and the breeze can be felt in 4 1, 2 1 or 3 2, and similarly you can see the pit here, the breeze is located in the neighboring cells also here. Now, how does he know whether there is a Wumpus? The Wumpus can be sensed by a stench. Stench is a strong smell. So, that is just a neighboring cell where the Wumpus is. Suppose the Wumpus is in 1 3, there is a strong stench coming from 1 2, 1 4 and 2 3. So, by this way the agent would sense whether there is a Wumpus in the neighboring cell or a pit in the neighboring cell. Now, the goal of this agent is to not hit with the pit or go into the same cell as the Wumpus, but in fact, he want to go into the cell where there is a gold. So, the gold here is located in 2 3. So, the goal the entire aim of this agent is to snatch this gold, but along with this gold he has to see that he is not eaten by the vampires or he does not fall into the pit, and the gold is sensed by a glitter, this is called glitter. So, for this problem, if you remember, we started off this course with PEAS, the performance, environment, actions and sensors. Okay. So, we will just describe what is the PEAS. The performance of this puzzle is 1000, 1000 for gold, getting the gold. He will get the point, the agent will get the points if he get the gold for 1000, minus 1000 for falling into the pit, minus 1 if he takes some action, and minus 10 for using an arrow. The arrow is like when the agent is at the straight line as a vampus, he can shoot the arrow and the vampus will while dead, before the vampus is dead, he would give out a big scream. So, by that sense, if he is screaming, that will be one sense by which the agent knows that he is dead. So, for using arrow it is minus 10. So, the environment here is going to be 4 cross 4 grid, where there are 4 on the row side and 4 on the column sides, and agent starts at 1 1. So, we normally say the column at 1 and this is this position. So, we call this as 1 1. Now, the action of this agent is going to be either he can move right, move left, move down, up, he can grab something, here it is going to be gold, and he can shoot. So, there are 2, 3, 4, 5, 6 actions, and the sensors are stench that is coming out from a cell because of the vampus, a breeze because of a pit nearby, the glitter because of gold in that particular scent, a bump because if the agent falls into a pit, there is a bump that can be felt, and scream when the vampus dies. So, these senses we are going to describe in terms of a pair, say a list which will consist of stench, breeze, glitter, bump and scream. It is in this order. So, first, second, third, 3, 4, 5. The first one refers to stench, B is for breeze, G is for glitter. Again bump, we can have a different name for this, which is bump, BP as bump and scream as S. So, these are going to be the 5 senses. Now, what are we going to do with this puzzle? The first thing that we will do is we will solve whether how we can detect the vampus is in 1 3 and there is a pit in 3 1 by our common sense method, and then we will use theorem proving exercise to do the same. So, let us start with agent at 1 1. Suppose we think that agent is at 1 1. Now, when agent is at 1 1, we will have the information as n, 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 n. Remember, each of these are going to be the senses where we said stench, breeze, glitter, bump and scream. Okay, these are the facts. When he is at 1 1, there is nothing here. Okay. So, the agent assumes that he can go either here or here. It is safe to go to 2 1 or go to 1 2. So, when there is nothing here, so agent goes to 1 2, 2 1. When agent goes to 2 1, if you check, agent is right here. When agent is here and here, this is the perfect way of mapping the values here, and this is again taken from Russell and Norvig, where you see this is 1, 2, 3 and 4, and this is again 1, 2, 3 and 4. The first one, this 1 1, this is 2 1, 3 1, 4 1, 1 2, 2 2, 3 2, 4 2. Okay. When agent goes to 2 1, this becomes there is no stench. Again I am writing here stench, breeze, glitter, bump and scream. These are the 5 senses. At this place there is no stench, but there is breeze. This also is not there. So, this would become there is nothing there, there is breeze, N and N. There is only breeze. So, if there is breeze, the agent thinks that okay, the pit may be in either in 1 1 or pit may be in 3 1 or pit may be in 2 2. Okay, when the agent is here, he would think that because the pit is nearby, either pit will be either here or 2 2 or 1 1. But in the earlier case, he already was in 1 1 and there was no pit in 1 1. See, this no I am mentioning as this symbol, okay, the inverse of 7, this indicates as no pit in 1 1. Therefore, pit should be either in 3 1 or 2 2. In 3 1 or 2 2, he comes to the conclusion 3 1 or 2 2. So, he does not want to take a risk of going to 3 1 or to 2 2. So, what he does, he goes to the safe bet. Earlier he said that in the earlier case we saw okay, this 1 2 is safe. So, now the agent turns back and goes from 2 1 to 1 1 and then back to 1 2. So, agent goes to 1 2. Now, agent is at 1 2. When agent is at 1 2, there is a stench coming. So, if we map the formula, again I am just writing that senses S, B, G, bump and scream. This stands for scream, the first one stands for stench. Now, at 1 2 there is only stench. So, it would be S, N, N, N and N. There is no breeze. So, when there is stench, he concludes that the bumpers may be in 1 1 here or 2 2 or 1 3. In one of the places bumpers will be there. Okay. Now, it is by the first instance when he was at 1 1 there is it was safe. So, he concludes that the agent concludes there is no bumpers in 1 1. Again I am indicating this is actually mentioning as no, there is no bumpers is 1 1. Therefore, bumpers should be in 2 2 or 1 3. But in the earlier case, this is the earlier case that we tried, we only said pit may be in 2 2 and there is nothing that is known of the stench. So, he also knows that the agent also knows that if there is a bumpus, if there was a bumpus in this location 2 2, he must have felt the presence by the strong stench when he was there already in 2 1. He visited 2 1, at that time there was no stench. So, if there is no stench, there is no bumpus also nearby. So, he concludes right now that there was no stench, since there was no stench in 2 1, he knows that no bumpus in this bumpus I am calling as W, no bumpus in 2 2. Therefore, he concludes that bumpers should be in 1 3. So, he concludes that bumpers in 1 3. Now, at the same time he also knows that because there is no breeze, this is on one side, and since there is no breeze in 1 2, no pit in adjacent sites. So, there is no pit in 1 1 or 2 2 or 1 3. So, there is no pit in 2 2. Therefore, by earlier case, earlier we said that the pit may be in 2 2 or 3 1. So, in this case, he 2 2 there is no pit, 1 1 there is no pit. Therefore, pit is in 3 1. So, we can conclude pit is in 3 1 and we can also conclude the bumpers in 1 3. Okay. So, we are in the agent position where we could determine that this is being done. Now, so the agent is at 1 2. So, we can also conclude bumpers in 1 3 that I did earlier, and also we concluded pit in 3 1. Okay. So, this is how we again I repeat, first the agent was here, he went to 2 1 and at 2 1 there was breeze. So, all he could conclude is pit may either be in 3 1 or 1 2. Now, to save bit, he again he does not go this side or this side, but he comes back and goes to 1 2. At 1 2 he feels a stench, and at that time he also understands that there was no breeze here. If there is no breeze, then there is no pit nearby, there is no pit here. Therefore, he concludes that there is a pit in 3 1. At the same time, if there is when he went at 2 1, if there is a stench, then he would have understood that there is bumpers hereby, but there is no stench here. Therefore, there is no bumpers here, in which case the bumpers would be only in 1 3. So, this is the conclusion that he comes with the common sense. Now, how can we do the same thing with the proposition logic? So, in proposition logic, how does he, and in order to finish off the entire thing. So, he goes 1 2, then comes back 1 1, goes to 1 2, and he understands that there is a bumpers here and pit here. Now, he goes to 2 2 and goes to 2 3 to get the goal. This is the aim. So, this is the completion of that story, which is from the common sense side. Now, how do we do that? Using proposition logic. Okay. So, in the proposition logic, we will have a set of knowledge base. In the knowledge base, we will write the proposition logic formulas, and using the formulas we will have a set of rules, and from the set of rules we will apply theorem proving and conclude the same thing. Okay. So, we will continue that in the next session. Right now, what we have done is right now what we have done for this session is I have introduced you to this logic puzzle, which is a bumpers world, and the goal of that agent is to get the gold in the location 2 3, and we solved it using our common sense method. In the next class, we will use theorem proving to do the same task. Thank you.